Gravity holds every aircraft to a strict binary choice. A plane must move forward to stay up. A helicopter must spin its entire lift surface to hover. Engineers at the British Ministry of Supply in 1957 tried to break this rule with the Hawker P.1127. They replaced runways with raw downward force. You assumed flight was a solved science, but the math for a vertical start is a trap. Subscribe now. This is the kind of video that gets buried. This design change killed 43 test pilots. Airfields are the greatest weakness of modern warfare. A runway is a 2-mile target that is easy to destroy. By 1950, the Royal Air Force knew their traditional jets would be grounded within hours of a conflict. They needed a machine that could hide in a forest and launch from a clearing. This is not fringe engineering. This is 70 years of unbroken documented record. The physics of this goal required a total reversal of aerodynamic logic. A standard jet engine produces thrust in one direction, backward. To go up, the Hawker P.1127 used the Pegasus engine. It had 4 rotating nozzles. These nozzles turned the entire power of the engine 90 degrees toward the dirt. Dr. John Fozard, chief designer at British Aerospace, who spent 30 years studying V/STOL vertical and short takeoff and landing, concluded that the margin for error was less than 2%. If one nozzle lagged behind the others, the aircraft would flip. The world was taught that flight is about speed. We were told that wings provide the lift. But in a vertical launch, the wings are dead weight. They provide zero lift until the plane reaches 150 knots. For the first 60 seconds of flight, the pilot is balancing a 6-ton metal box on 4 pillars of hot air. This is called the hover transition. It is the most dangerous minute in aviation history. Institutions often filter the reality of how close these projects came to total cancellation. The United States and Britain spent $500 million on a design that most engineers called a physical impossibility. They were fighting the ground effect. When a jet blasts air at the ground, that air bounces back up. It creates a vacuum that tries to suck the plane back down. The engine is literally fighting its own exhaust to stay alive. This is not a simple upgrade to a plane. It is a machine that ignores the way air is supposed to work. Most early designs used separate engines for lift and forward flight. That failed because the lift engines became useless weight once the plane was moving fast. The British chose a single-engine solution. It was elegant on paper but a nightmare in the cockpit. The Pegasus engine was the first to successfully rotate its own thrust while in flight. Before we go further, drop your answer in the comments right now. Do you think vertical takeoff is a necessary evolution of flight, or is it an expensive engineering ego trip? I read every comment. And this one is going to split the room. Dunsfold Aerodrome. October 1960. Bill Bedford climbs into the seat of the XP-831. He is a veteran pilot with thousands of hours in the air. He wears a heavy flight suit and a silver helmet. The air is cold. A low rumble shakes the tarmac as the Pegasus engine wakes up. Bedford is not moving forward. He is sitting on a concrete pad with 2 thick steel cables tethered to the landing gear. These are dead man's ropes. They are designed to catch the plane if it loses balance. He moves a single lever next to the throttle. The 4 nozzles underneath the fuselage rotate downward. Ground crew members stand 100 feet back. They squint against the sudden storm of dust and heat. The plane begins to vibrate with a frequency that rattles the pilot's teeth. Bedford slowly increases the power. The XP-831 does not roll. It lightens. He feels the tires leave the concrete. The aircraft is now a 5-ton pendulum. He has no traditional control. The rudder and elevators are useless because there is no wind passing over them. He must use puffers, tiny valves at the nose, tail, and wingtips that bleed air from the engine. He is flying a jet with the controls of a spacecraft. Suddenly, the nose pitches up. The engine swallows its own hot exhaust. This is a hot gas ingestion event. The engine loses power because hot air is less dense than cold air. The plane drops 6 inches and the tether cables snap tight. Bedford's hands move with mechanical precision. He stabilizes the hover. He stays 3 feet off the ground for 20 seconds. The noise is a physical wall. He looks at the horizon. It is perfectly level, but the ground beneath him is a blurred vortex of heat. He shuts down the engine and the plane settles onto its struts. He climbs out and his legs are shaking. He has just performed the first vertical hover of a jet in history. But he knows the truth. The machine is not under his control. It is barely agreeing to stay upright. Bedford records his notes in a small leather book. He describes the craft as a wild horse. He realized that if the pilot stops thinking for even 1 second, the physics of the hover will kill him. He was right. The hover was not the miracle. The miracle was the transition. In 1961, NASA researchers at the Langley Research Center conducted the first comprehensive wind tunnel tests on V/STOL stability. They used a full-scale model of the airframe to measure what happens when a jet moves from a vertical hover to forward flight. This is the exact moment where the laws of physics cross paths and try to destroy the vehicle. What they saw was not a smooth glide. The sensors revealed a phenomenon called wing drop. As the nozzles rotate from the vertical position toward the back, the lift from the engine decreases. The wings are supposed to pick up that lift as speed increases. But there is a dead zone in the middle. For a window of about 15 seconds, neither the engine nor the wings provide enough force to support the weight. This is a structural void in the air. Dr. James Campbell at the NASA Langley Center, who spent 25 years studying transition aerodynamics, found that the turbulence created by the rotating nozzles actually blocked the air from reaching the wing's leading edge. This is a self-inflicted stall. The aircraft is literally moving too fast to hover, but too slow to fly. The pilot is falling through a gap in the math. But that is not what stopped people cold. This is. The team analyzed the crash data from the early Kestrel and Harrier prototypes. They recovered data from flight recorders that showed a recurring failure in the reaction control system, or RCS. These are the puffer jets at the wingtips. The lab results showed that during high-heat hovers, the metal in the valves would expand. If one valve stayed open for 0.5 seconds too long, the plane entered an unrecoverable roll. The data showed something even more specific. They found traces of re-ingestion erosion on the turbine blades. When the jet is near the ground, it kicks up a fountain of grit and superheated air. This air enters the intake at 400 degrees Celsius. Professor David H. Hickey at the Ames Research Center examined these patterns. He found that the engine thrust dropped by 10% within seconds of liftoff. Before we get to the discovery of the vortex ring state in jet engines and why the Navy almost banned the aircraft after a single test on a carrier deck, subscribe now. What comes in the next 2 minutes is the part most people never hear. You need to be here for this. And then came the passage no one expected. The wind tunnel found a massive aerodynamic suckdown force at the bottom of the fuselage. It is a low-pressure zone created between the ground and the belly of the plane. The scans suggest this force is equal to 500 kilograms of weight pulling the plane toward the Earth. In 1968, a flight test at Patuxent River analyzed this specific area. They found it created a ground effect trap. This is a problem for mainstream aviation. Usually, ground effect helps a plane stay up. But for a vertical jet, the fountain of air hits the belly and creates a vacuum. The official reports say pilots had to use 105% of engine power just to break free of the dirt. Yet, here it is. It is a design that requires the engine to work harder the closer it is to the safety of the ground. The third finding is the one that changed everything. Underneath the aircraft during a hover, the air is not moving in a straight line. The team found a toroidal vortex. This is a donut-shaped ring of air that circles back into the top of the engine. It contains the poisonous exhaust from the previous second of combustion. This air has no oxygen. It is a dead gas. There is only one way a jet engine survives breathing its own death. The pilot must pitch the nose forward exactly 5 degrees. This moves the intake away from the vortex. Dr. Campbell stated that the margin for this tilt is consistent across all early vertical designs. It is a narrow band of survival trapped in a cycle of fire. This confirms the pilot was not just flying. He was balancing a chemical reaction. You have seen the footage of these planes hovering. It looks like a calm feat of power. But the data shows the cockpit is a site of constant correction. It has 3 separate control systems fighting for priority. It has a gyroscopic stabilizer that runs at 10,000 revolutions per minute. These systems were designed for a specific purpose. They were built to keep a heavy object from succumbing to its own exhaust. This is the first modern mirror moment. We think our current technology is stable because it is automated. We think the F-35B solved these problems with software. But the physics remain the same. The computer is just moving the valves faster than a human could. We are still balancing a 15-ton metal box on a pillar of fire. The scans also revealed a strange anomaly in the engine's center of gravity. There is a large, heavy rotating assembly that creates massive torque. It is called gyroscopic precession. If the pilot tries to turn left, the physics of the spinning engine tries to push the nose down. The math is perfect, but the feeling is wrong. The plane resists the pilot's will. This is the payload. Vertical flight is not a triumph of the wing. It is a triumph of the engine over the wing. It is a machine that forces the air to do something it does not want to do. It survived the 1960s because we were willing to lose pilots to find the gap in the math. And then came the revelation that changed the military's entire strategy. The technical data is cold. Numbers and wind tunnel results do not capture the weight of what happened in those cockpits. Look at the puffer valves again. They are tiny openings at the very edge of the wing. Each one was the only thing keeping a human being from an inverted impact. A pilot spent months training his brain to ignore every instinct he had ever learned. He had to trust that an invisible jet of air would hold him up when the wings felt dead. You have felt this. Most people have felt this at least once. You are in a transition where the old rules no longer apply, but the new ones haven't taken hold yet. There is a specific kind of loneliness in that gap. It is the silence of the controls when you are suspended between two worlds. This state calls for a total surrender to the machine. The men who flew these were not just pilots. They were tightrope walkers in a hurricane. They sat in the heat for minutes that felt like hours. They listened to the engine scream at the limit of its endurance. They lived in the smell of burnt kerosene and ozone. They were the only bridge between the age of the runway and the age of the clearing. Think about the moment the plane finally began to move forward. The vibration would have changed. The nose would have settled. The wings would have suddenly caught the air and started to lift. The transition was a birth. The pilot stepped out onto the tarmac after a mission, and the ground felt alien. He had just spent an hour proving that he didn't need it. This is the universal human experience of the leap. We all face moments where we must trade our stability for a chance at a different kind of progress. We find ourselves balanced on a pillar of our own making, wondering if the engine will hold. The vertical jet is a physical reminder that balance is not a state of rest. It is a state of constant, violent correction. It tells us that reaching the height is not the victory. Staying there is. The valves did not fail because they were built for the struggle. The pilots did not quit because they were meant to find the answer. This aircraft is a message sent through the history of flight. It is a statement that the sky does not have a floor. Most people have felt the gap between the stability they were promised and the chaos they actually navigate. If this is landing for you, if the idea of a high-stakes transition resonates with your own life, you are not alone. You are exactly the person this was made for. Drop a comment. Tell me where you are with this. The pursuit of vertical flight should have ended the age of the aircraft carrier. If a jet can land on a small patch of grass, it does not need a billion-dollar floating runway. Yet, for decades, the full capability of these machines was downplayed. This is not the result of a secret plot. It is the result of institutional selection. Military organizations protect their existing investments. When a discovery threatens to make an entire fleet of ships obsolete, the institution often chooses to slow the progress rather than rebuild its entire strategy. There are three concrete reasons this technology was suppressed. The first is the problem of logistical weight. Our current understanding of air power is based on the tail. This is the massive support system of fuel trucks, spare parts, and specialized mechanics that follow every squadron. A vertical jet hiding in a forest requires a mobile supply chain. This contradicts the work of thousands of logistics officers. In 1965, the Tripartite Evaluation Squadron team of British, American, and German pilots proved the concept worked. They launched jets from muddy fields and car parks. The report was filed away. By making the logistics look impossible, the institutions could keep the jets tied to traditional bases. The second reason is strategic exclusion. The Navy viewed the vertical jet as a threat to the supercarrier program. A carrier is a symbol of national prestige and a massive budget item. If a small, cheap helicopter carrier could launch high-performance jets, the argument for the $13 billion Gerald R. Ford class disappears. In 1972, the U.S. Marine Corps had to fight their own Navy to buy the British-made Harrier. The Navy leadership used safety concerns to block the funding. They focused on the high accident rate of the early hovers to hide the true fear, the death of the flat top. The third reason is politically untenable. If the vertical takeoff was fully mastered, the geometry of global borders would change. Air power would no longer be tied to fixed locations that can be monitored by satellites. It would become invisible. Institutions do not like to lose the ability to track the enemy. They prefer the predictable runway because it allows for a controlled theater of war. We must look at one specific event. 1961, the Hawker Siddeley P.1154 project. This was supposed to be a supersonic version of the vertical jet. It was the most advanced aircraft design in the world. In 1965, the new British government cancelled it overnight. They claimed it was a cost-saving measure. At the same meeting, they decided to buy traditional American jets instead. They chose a 20-year-old technology over a 10-year leap. They wanted a predictable budget, not a revolution. The AI used to analyze the flight logs of these early programs has no career to protect. It has no budget to defend. It was asked to identify why the supersonic P.1154 was abandoned. It surfaced a pattern of institutional inertia. It showed that the plane didn't fail because of its engine. It failed because it was too efficient for the bureaucracy to handle. You see the pattern. The breakthrough was not a mistake. It was simply categorized as too risky until it was no longer a threat to the status quo. The blueprints were moved to the back of the archive. The test data was stamped as experimental for 40 years. But the physics does not care about the budget. It continues to offer a way out of the runway trap. It waits for the moment when the need for survival becomes stronger than the need for institutional comfort. Now I understand why this happened. The world was not ready for air power to become truly decentralized. But the data is now public. The success of the F-35B in modern conflicts has forced the secret out. The silence of the Navy is no longer enough to keep the vertical jet in the shadow. The ghost of the P.1127 is no longer confined to military museums. It has moved into our cities. One specific finding in the early stability logs describes a distributed lift architecture. This is a system where power is spread across multiple points to create a stable platform. The text of the original British patent describes a world where the tyranny of the runway is finally broken. Does this sound like it was written in 1957? Or does it sound like something from this week? We are currently witnessing the rise of the eVTOL electric vertical takeoff and landing vehicles. We see companies promising air taxis that will hover above our traffic jams. These modern designs are sold as a new invention. In reality, they are the second act of a play that began in a cold hangar in Surrey. They are using the same puffer logic and the same transition math that Bill Bedford mastered 66 years ago. These flight logs were written by hand by engineers who had no concept of lithium batteries or carbon fiber. They used slide rules and grease pencils. Yet, they solved the problem of the vortex ring and the ground effect vacuum before we had a common language for software. They mapped the edge of the sky with nothing but bravery and a mechanical lever. The direct contrast is clear. We have replaced the pilot's instinct with a flight control computer. We have swapped the roaring Pegasus engine for silent electric motors. But the physics has not changed. The air still hates to be pushed downward. The vacuum beneath the belly still tries to suck the vehicle to the ground. And with hope, not darkness. The history of vertical takeoff is a story of a successful escape. It proves that we can break the oldest rules of our environment if we are willing to build a new kind of machine. The F-35B is now landing on small amphibious ships that were never meant to carry jets. The wild horse has been tamed. The ancient, or rather, the mid-century source closes with a vision. It describes a future where every village has its own connection to the sky. It envisions a world where distance is no longer measured by the length of a concrete strip. This is the promise of the vertical leap. It is the realization that the most important part of the journey is not the speed of the flight, but the courage of the start. This video covered the mechanical struggle to rotate thrust and the institutional weight that kept vertical flight grounded for decades. But it raised a question that goes deeper. What happens when this same physics is applied to the vacuum of space? That is what the next video answers. Subscribe and turn on notifications. The next video reveals the secret 1960s lunar lander tests that were intentionally scrubbed from the public record. One specific design flaw almost left 2 men stranded on the moon. You will not want to miss what comes next. The physics of vertical takeoff is the story of human willpower fighting a pillar of fire. It is not just about planes. It is about the moment we decided that a runway was a choice, not a requirement. Drop your answer below. If you had the chance to commute in an automated air taxi today, would you trust the transition math, or do you prefer keeping your feet on the ground? I read every comment. This one is going to split the room. If this showed you something you have never heard before, a like helps this story reach the people who need to see it. It signals that you value research over sensationalism. Subscribe and turn on notifications. The next video goes directly into the Project Morpheus files. We have the internal memos regarding the engine failures and the real reason the test pad exploded in 2012. Subscribe and you will not miss what comes next.